Okay, the last section for our static electricity discussions deals with capacitance and dielectrics. Capacitors are little mechanisms that are put into an electronic structure to hold charge after the circuit is closed off. So the static electricity in that electric field between the two plates that they have, and usually they're just plates, rectangular plates, stay for a while to allow, in case it needs to be restarted or it has another function attached to it. I put some examples on here of how we use these things. There's a ton of them. This is, so I'll just read it real quick. Uses for this are energy storage electronic devices, particularly like cell phones and Game Boys and all that. Power factor corrections in motors and transmission lines, which I did not know about. Now I found that fascinating. Sensors, the car sensors in which certain things go off and some things that is not going quite right. They're able to follow the static electricity in that into some kind of monitoring system. Conditioning of power supplies, coupling by blocking DC current in loudspeakers. I think there's other examples of that too. And what that means is when you, in loudspeakers, you have an AC flow to it, but every once in a while you get a charge of a DC flow through it, and it can damage the loudspeakers. So they are there to kind of block that from going into the entire electrical mechanism of the loudspeakers. Radio tuning, pulse power and weapons, which kind of freaked me out when I was reading that. Was rather fascinating stuff though. Bypassing power supplies, again, I think that has to do with the AC versus DC systems. Timing elements and speakers and diodes. IT signal processing and smoothing current in cell phones and computers. Again, getting back to that that AC-DC conflict going on in electricity. So, how do we measure that? Well, the main idea for this is being able to compare the amount of charge you have per volt. In fact, this is the formula for capacitance. Now, it gets a little tricky here because we use capital C for the dynamic of capacitance. This is not to be confused with the capital C for coulombs in charge. So you got to be really careful of that. Charge here is Q, which is measured in coulombs. This C here is coulombs. In fact, I'll just write that right here, because this is describing the label of capacitance. And of course, V stands for volt. So coulombs per volt is technically what you're measuring in your static electricity within your electrical system there that's holding the charge. They simplify this, probably get rid of this whole coulomb thing because people, I'm sure, got confused between that capacitance, so they gave it farads. And named after Michael Faraday, was a very famous electromagnetic chemist and physicist and scientist, just a brilliant man. He didn't do math very well, evidently, but he sure liked to do this stuff. So a couple examples I gave for the calculations for this, or for this particular concept here, we have the one here. Suppose we have a 12-volt battery hooked up to the system. So this is a DC system. We have a capacitance of 2 microfarads. And again, the labels for SI means the same for electrical as well as mechanical physics. So the formula C equals Q over V, as we're trying to figure out how much charge is, how much static electricity we have in that capacitor. So we simply take the capacitance equals Q over 12.0 volts. Algebraically, just multiply by 12.0 volts. And you get 2.40 times 10 to the negative 5th farads, or 24.0 microfarads. Again, farads, coulombs are extremely large quantity of electrons, so it is not going to be rare to see that we use micro and nano a lot when dealing with capacitance. Now, they found that they can improve capacitance by putting in something between the two plates. And they'll have a series of plates, pairs of plates within the mechanism. And if you let just the air in there, it tends to dissipate rather quickly. So they'll put something inside or between the two plates made of different materials. Now there is a chart in your book that you're going to need to refer to. It's on page 579. It talks about those substances that they put between the two plates that actually holds the static electricity, and they are called dielectrics. So let's take the example I put on your script for you. The original capacitance, before they put the dielectric in it, of this particular capacitor is 43 nanofarads. Then they decided to put in Pyrex glass, a little sliver of Pyrex glass that's going to fit neatly between the two plates. And this little K, and I mean miniature K, is the dielectric constant that you will find on page 579. For Pyrex glass is 5.6. There is no label, it's just a multiplication factor. How many times more capacitance you can have? 5.6 times more with the Pyrex glass. So your formula here is the capacitance of the new system equals that cute little K. It's so cute that H, don't you think? Times the original, it all stands for original, capacitance. So 5.6 times 43.0 nanofarads gives you 2.41 times 10 to the negative 7 farads. Or if you want to go back to the nanofarad, then you could, 241 nanofarads. You could have left, instead of changing over to, well, you could have left it there to say 241 nanofarads, or you could have put 43 times 10 to the negative 9 farads. Either way, you get that value for an answer. That's all there is to it. So, the practice problems for this, you will have 5 of them, again, with different, I've got 3 regular capacitor problems, and I got 2 dielectric problems. So, make sure you have your book handy when you do those last 2 problems. Have fun.